Okay, so again, Ms. Zhen, I'm a faculty member in the Universidad Diego Portales, so in Chile. So in this way, even I don't look like a Chilean, so welcome everybody to Chile. Today I'm going to talk about eruptive flows from the VVV survey team. And most of this work in the collaboration of the VVV survey, and also expert in star formation. So it's always a great privilege that I'm giving a talk right after Lee because I don't have to do any introduction. There's nobody else can do such an informative talk after Lee. So, but I also want to re-emphasize some of our motivation here. First of all, we want to understand the overall picture about stellar mass assembly. So episodic accretion is an important of the stellar mass assembly because during this stage, the star gather of mass. And from the observational side, to determine the duration, the amplitude, and also the reoccurrence rate of this event is important to understand how they contribute to the picture. Also, we want to understand the star interaction, whether these outbursts are triggered by a giant planet or triggered by the disk, and what is the consequence of this outburst to the planet formation. And we also want to explore different physical methods that can explain different observational features from this outburst. So as an observer, my job is to find more to try to explain it. So as we know that the outbursting stage of a young star is relatively short comparing to the millions of years of Permian sequence evolution. So these targets are difficult to find. So the occurrence rate estimated by several works, including Lin's work, 10 to minus 4 per year per star, or 10 to minus 5 per year per star. So it is extremely difficult to find, so we need surveys to increase our parent sample. On the other hand, we want to have long-distance surveys that can capture not only the rising stage, but also the bursting stage and the decaying stage of the event, so we can have a full picture of the event. In the end, we try to go to earlier evolutionary stages because they have heavier disk, they have higher density in the disk, so they can trigger more interesting instabilities inside the disk. So far, there are 3 really productive surveys, including Gaia in Eruptive, in the near-infrared, and NEO-WISE infrared. CD before and after the outburst, and you can see that the dramatic change in all the wavelengths. So you are actually able to find those outbursts in 3 different surveys. And today, according to the title, I'm going to show more about the results from the VVV survey. The VVV is an acronym of Vista Variables in the Via Lactea. The original survey started from 2010 and finished around 2015. We are targeting the galactic bulge and part of the inner galactic disk. Most of the VVV survey has been done in the near-infrared K-band with a cadence about several tens visits per year. After 2010, we started the VVV extended survey with a larger area, but smaller cadence. So now we have about 1 data point per year. The total number of sources in the VVV variable sources, among them there are 100,000 young stellar objects. So VVV is a great tool to actually help us on duration outburst among young stars. Our Eruptive YSO team, led by Professor Phil Lucas from Hertfordshire, and also Carlos has done a lot of mental work for our survey. So we have been looking for eruptive YSOs, and we've hundreds of them published in several photometric catalogs. And then my work mostly focused on the spectroscopy following this eruptive event to confirm whether there are FE arrays, the EX arrays, or there are something. And then the third step of our study is to study individual event. We try to use multi-wavelength light curves to describe the detail of this event, and then to provide more information to theoretical astronomers. And the next step is the statistical analysis. I think Carlos will show more about it in his talk. So today I'm going to show some of my work that recently published. So earlier this year, using the VV data, we were able to find a group of new FE arrays, around 15 of them. And then On the left-hand side is the K-band time series of this event, and you can see a unique feature here is the sharp rising stage marked by the green lines. However, we do see some diversity here. As Lee mentioned, there are some of the outbursts that are not as strong lasting. Some of the FURIs, for example, the bottom left one, the bottom right one. So the star rapidly decayed right after we suggest that we have different mechanisms maybe to trigger this outburst. However, we do see that their spectra look basically identical, and this is how we identify this event as FURIs. But you know, it doesn't mean that all of them have really high mass accretion rate or something. They just look similar here, what we see in the X-shooter spectra. We also obtained the NEO-wise color and amplitude information about this event in the mid-infrared, and we are able to compare the FURI type event, which has the absorption features in their X-shooter spectra, compared to other long-lasting outbursting events. Not talking about the short-lasting EXORs, but about long-lasting. And we found systematically FURIs have higher W2 band amplitude, suggesting that it can thoroughly hit the inner equation disk. And on the other hand, we do see that FURI, systematically, they have faster rising timescales compared to other type of eruptive event, suggesting they can reach the photometric maximum quicker, and the outburst is stronger compared to other types. Although it is not a definite conclusion, see some blending here, and also this one is VVV 721. So this has a 2,000 days rising time. Okay, one of the individual case we published here is L22278. So you can see the multi-wavelength light curve here from Gaia in the yellow, and then VVV in black, and then mid-infrared light curve in orange-ish color. So this event has been captured by all the 3 surveys I just mentioned. And then Gaia, it has an astonishing 7.2 magnitude eruption in Gaia. And then as we can see here, maximum these things start to, and then, but all 3 Gaia bands. If we see in the K band from VVV or in the mid-infrared, this thing didn't really go through the decaying stage, but this thing happened in the Gaia wavelengths. According to the color, it is caused by the enhancement of extinction. And then after a few years, this thing started to graduate. And then we do see a delay similar to Gaia 17 that rise slightly earlier than the Gaia, but then it is not like 1,000 earlier. Here is about 100 days earlier, suggesting that the outburst is initiated a little bit closer to the star, but not right next to the star. We're trying to find theoretical explanations of this target, and thanks to Sergey, and we are looking forward as the extreme evaporation scenario that the outburst is a giant planet around the inner edge of the circumstellar disk. And then after the outburst, the envelope of the planet got evaporated and then feed back to the star and creates a continued outburst here. Another object we are now is an infrared outbursting source, VVV WIT13. So WIT means what is this? Because we have no clue about it right now. So, and you can see we have a lot of objects without clue. It's already number 13. So this object has an outburst around 1,500 days, which is between FURIs and the EX. However, when we take a spectrum during relatively brightening stage using X-shooter, we see some features here and here. So in the K band, we recognize this is CO as most of the FURIs, but with a lot. But what is going on in H band? We have been asking this question to a lot of colleagues in Young-Zilla objects. We do not find the answer, but when we talk to exoplanet people and also to red nova, so Yurchenko and Kaminsky told me, it is aluminum oxide. It's typical for those people. So actually, this is a nice fitting from the XMO database from UCL that they provided to us. We can fit the aluminum oxide absorption with a 600 Kelvin temperature. So it's a really cool disk stuff. And we also see the CO here. However, after 2 years, when we revisit this object, aluminum oxide just disappeared. And instead, we see the emission from the molecular hydrogen indicating launching of an alpha. So we're still working on this object. Another one is utilizing VVV near and eruptive YSO, which is a repeated EXORY. So first outburst we detected in 2014 using VVV data, we marked it as EXORY. And then after 10 years, this year they had another outburst. According to the Atlas data we just taken last week, the outburst still ongoing. When we took the spectral observations using Magellan and SOAR, we can see a lot of emission features here, and to confirm that it is an EXOR type. With several observations after the outburst, we do see some variation on the emission line profiles and also the ratio between different emission lines, suggesting some interesting physics going on. And this is collaboration with Mike Kuhn from University of Hertfordshire. I will skip this because I'll show it in the afternoon. So to wrap up our talk, so we have some challenges and future works in our group. First of all the VVV, not only VVV and VVX, all the VVV data is in the past ongoing. So especially VVV data, it lasts until 2019. So whatever we found from VVV is in the past. We need more photometric observations to know the duration and to know the evolution of this event after the outburst. So photometric revisits are important. So far, we're planning for some near-infrared photometric and spectroscopic revisit of these objects and to cover a larger scale area so we can have a new light curve of this event. And of course, in the future, Rubin will be the future of our variable star community. We need to use community brokers and also outlier detections in these eruptive YSOs. So according to the engineering, it's not easy to characterize. So we need to work on that. And then follow-up observations can be difficult in the optical. Those optical sources are relatively faint, especially the ones detected in and near-infrared observations, and also multi-wavelength observations 3 to sub-millimeter to give us a full scenario, a full picture of objects. And I want to introduce our team of rowdy planetary nursery, the China-Chile Joint Research Project, the Chinese Academy of Science. Our project focuses on spectroscopy confirmation of eruptive added YSOs. We also want to study the scenario of planets and their consequences on the accretion rate of the system, and also if we see some different of the young planet around young stars will be interesting. And one of the work done by my co-I, T.S. Montesinos, is this simulation that he showed that a planetary mass object on the eccentric orbit can create this torque series in the inner accretion disk, which can create future outburst. So here are my take-home messages. I hope I convinced you that large-scale photometric surveys are powerful to find those eruptive YSOs. So far in the VV team, we looked at about 50 with spectroscopic confirmation, and 20 of them are a prioris. We do detect some diversity on the light curve morphology, which indicate different trigger mechanisms. And rapid follow-up observations on Chilean-based telescope could be the future after we have more samples from Rubin. In the end, this workshop I want to learn more about eruptive so we collaborate together. Thank you.
Thank you very much, Zhen, for this excellent review. Questions from the audience? Yes. Kami-san.
Okay, thank you, hard work. Basic question. So you say you can I make sure of your definition of FEORs? Looking at your light curve, how can identify these are FEORs, not the types of outgoing sources?
This is a good question. So it's basically identified by 3 characters. The first character is they have to be young star. And then the second character is we detect a large outburst, either in optical or infrared. And then the third character is actually from the spectroscopy observation, we are not looking at a hot star. We're looking at a cool but bright inner disk.
Do you have any definition about criterion about how large? So I mean yes.
So we select the object larger than 3 magnitude in K-band. Of course, they could be smaller ones, but existing spectroscopic features, but we haven't gone through it. VVV, if you select delta K larger than 3, you have few thousand objects, but if you lower your selection limit, you have more target, and we need more PhD students looking at it, basically.
Thank you.
Follow up on that question. So from the infrared spectra alone, can you be a little more specific about what you use the object as definitively young, as distinct from many kinds of evolved objects in binary systems that also go accretion, brightening, symbiotic stars, things like that?
That's another important part. Thank you, Lynn. So here, so usually, if you see a large outburst, and then you see this kind of cool spectrum. There are only basically two options. One is a young star, one is an old star. But for old stars, we usually see 13 CO absorptions around here. So all of this object doesn't really have this 13 CO absorptions. And we see 13 CO absorptions here in the and this object. So that is one of our criteria.
Thanks very much for the nice talk. I have a very basic question. So based on your experience with spectral follow-up, so do you think all of the FEORI-like object are FEORI on this object?
No.
So there's something else which could look like FEORI on this object spectroscopically?
Yes. Again, I don't have time to show all of our target. So if you see here, a lot of the objects we found actually they're not shown in the red color. They are in the blue and brownish color. So all of these targets are long duration outbursts that if you only look at the light curve in K-band, you can't really distinguish them between them and FEORIs. After we took the spectroscopic observation, some of them is full of emission lines instead of the absorption lines like FEORIs. So they're still controlled by the magnetic field, the accretion. So they are not FEORIs.
So when you say emission objects, do you really think it's magnetospheric emission, or it actually just be strong wind?
Good question. We see Brca gamma and Passon beta emission, which is usually seen, and then, but we also see a lot of molecular hydrogen, so it could be outflow. So we also call them outflow dominated if their molecular hydrogen emission is particularly. But some of them we also see a hot inner disk bandhead emission feature. So we see that there is a hot inner accretion disk. Yes. Yeah.
So for the source, I think the WIT or what mean that here in the H2 appear. Do you know what's causing that? Like where the CO is going, or like where the H2 is coming from, or anything like that?
We are still working on it. CO didn't disappear, so the aluminum side disappeared, and the CO become shallower. So we're seeing the aluminum is only 600 Kelvin, even though when we feed the CO is 1300 Kelvin. We're thinking maybe this is come from a disk stuff, but after it got cooler, after 2 years, you can see the light curve there. So the second iteration was taken last year. Actually, the star is already faded. So which means, you know, the disk is not warm enough, so you can't really detect those absorption features properly. But CO still persists because it's located closer. But we still, and because in the previous works, this aluminum oxide acted around red novia. Red novia is a stellar merger. So probably, but then our time scales is quite different than stellar mergers. Stellar mergers faded in about 100, and this one has because it has accretion disk. So probably it's a star-planet merger during the pre-min sequence, but we're not 100% sure yet.
Just one more question. Yes, over there, and there is it from one of our online participants. The shape of the second outburst of the repeating XOR similar to the first?
No, it's not similar. So if I can show you this slide, so we don't really detect the secondary burst yet, but then we do see a rise of the magnitude in G band. So probably in a few years it can go up to 10 times. I'm not sure.
Thank you. We have time for 2 more questions.
Okay. Sorry. Yeah, this one. Yeah. So it's another good question because the first outburst we didn't do light curve. Yeah. So far we have the Gaia light curve covering the rising stage and also Atlas covering the rising stage. So we think it should be similar, but I cannot say they are similar without the evidence. So we are waiting for this object to get faded so we can estimate the duration.
Thank you.
Just if you go back to this WIT13 source again. Yeah, just to comment that this is important, I think, for models. Because some of the models actually do predict that you should be seeing cool disks with, you know, this sort of temperatures. But I would say either in quiescence, so pre-outburst or post-outburst. So I don't know if this is because you're already looking at it on the decaying phase or not, but yeah, because in quiescence, the disks in these models is such that essentially you have an inner wall, so you don't see hot temperature disk, but you have a cooler disk which dominates the emission. So you could be seeing that, and perhaps that will help to test.
Okay.
A very quick question. In this source, you show that you found repeated outbursts. Is there any hint that indicates by there?
Repeat.
Yeah, in that source, do you think it's a binary?
From the target itself, we didn't detect the double-peaked absorption features during the quiescent stage, so it's not a spectroscopy binary, at least. And but it would be a hot Jupiter mass object, but you know, with eccentric orbit.
Okay, thank you very much.
I'll have to ask you to postpone that question for the discussion. Please put it on hold. And let's thank Zhen for this great review on the new discoveries. now we welcome